So today I want to talk to you guys about properties of matter. Okay. Now, properties of matter, there are two types. First one is chemical properties. Okay. This is how a substance reacts with other substances. So two things, when they react together, how they react, that's a chemical property. This actually can't be observed, though, without reacting it and changing it into something else. So, for example, a chemical property could be toxicity, oxidation states, heat of combustion, flammability. All right, if I take something and it's flammable, like paper, that is a chemical property of paper. It can burn, it can react with the oxygen and turn into carbon dioxide. But water is not flammable, so that is not a chemical property of water. It's a way to distinguish them. Okay? Properties are things, characteristics of these substances. All right? Now, there's another type of property. It's called a physical property. Now, a physical property is any characteristic about the substance itself, which can be observed without changing what it is. You just kind of look at it and be like, yep, I know this about it. All right? So, there are two types of physical properties: extensive physical property and intensive physical property. So, not only do we have two types of properties, chemical and physical, but physical can be further broken down into extensive and intensive. An extensive physical property depends on the amount of material that I have, so the sample that I currently have in my possession, whereas the intensive physical property, that depends on the type of material it is. It can be used to identify it or characterize it, but it doesn't matter how much of the material I actually have. So, a couple of examples to kind of show you the difference between these two. Extensive physical property. So, some examples here. Its shape. I can take paper, for example, and it is shaped like this, or I can make it shaped like this, or I can fold it into an origami thing, but it doesn't affect the fact that this is paper, right? Doesn't really matter how much of it I have. So temperature, or the amount of energy it has, is another one. Current state, it's a solid, okay, state of matter. Its length, its mass. Now, mass is the amount of matter in it. Okay, we can measure that. And the volume is going to be different too. The space that takes up. That's what volume is. Those are all extensive physical properties. Intensive physical properties, on the other hand, it doesn't matter how much I have. This includes color, boiling and melting point, density, right? Surface tension, specific heat capacity, solubility. There's a whole bunch of them. So, for example, let's say I had two pieces of iron, maybe a bolt and a nut. Okay, now they would have different masses, different volumes. They would be different sizes. There's a whole bunch of things about them that it's different. But both of them are made out of iron, so they have the same color. They would melt at the same temperature. They have the same density. They are both magnetic. All these properties that they would both share because they're made out of iron is an intensive physical property. Anything that they have just for being that specific item, then like the shape or anything, that is an extensive physical property. This is not an exhaustive list, by the way. Okay? So intensive physical properties, extensive physical properties. So to kind of break this down, properties of matter. You have chemical properties and physical properties. Chemical property is evident when you do a reaction and it gets destroyed. Physical property is evident when you just look at it, all right, or measure it. There are two types of physical properties, extensive and intensive. Extensive depends on how much you actually have. Can't be used to identify it, though, like the mass or the volume. Intensive, though, can be, because all of that material is going to be the same. They are going to have those same intensive properties. Okay? Next topic, the particle nature of matter. The idea here, a long time ago, is that all matter consists of tiny particles, which we call atoms and molecules and ions and a whole bunch of names for them. All of the properties of matter that I just talked about can be explained by how these particles are interacting with each other. So if we were to actually be able to zoom in, we'd be able to see these individual atoms and molecules, these particles, and how they interact with each other kind of determines what we can actually see in the real world here. Now, this idea was first proposed by a man named Democritus, and I'm going to let Bill Nye explain this.
Imagine cutting a piece of cheese in half. Then, in half again. And in half again. And 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 again. Eventually, you'd end up with a piece too small to cut. There'd be no knife sharp enough. Tiny, tiny pieces that couldn't be broken apart any farther. They'd be unbreak-apartable. We call them atoms.
So Democritus was a Greek philosopher who lived over 2,000 years ago, almost 2,400 years ago. He's the first person to seriously propose that matter was composed of these tiny particles called atoms. This is from the Greek word atomos. All right. Now, his ideas weren't much accepted at the time, but he believed that atoms couldn't be created, you couldn't destroy them, couldn't divide them. Each material was going to be a unique type of atom, and there were just infinite kinds of these types of atoms, so every material was its own little tiny mini particle. And these atoms were mini versions of the whole thing. Okay, so the way he imagined them being, like a stone was made out of tiny little stones. Fur was made out of tiny little furs. Water was made out of tiny little slippery drops of water that so small you couldn't even see. Iron was made out of tiny little chunks of iron, and they were all pokey, so they stuck together. Okay, that was his idea. He came up with it over 2,000 years ago. Why wasn't it accepted until modern times more accurately? Well, you may have actually heard of this next one before. This was from Aristotle, who was around the same time period, and most people thought that this was a better idea of explaining things. He's responsible for the 5 elements: earth, fire, air, water, and then there's the 5th one is ether. Okay?
Aristotle's cosmology was abstract too, but he attempted to make sense of observations about the world. He crossed those same 4 elements, plus a new anti-void called the ether, with 4 physical sensations: hot and cold, dry and wet, and used these to explain everything. Earth was the heaviest element, so it was the center of the cosmos. Water was lighter than Earth, so oceans rested on top of the Earth. So far, so good. Air's natural state is above water. That also checks out. Fire is on top of air, which is a little weird, but it does go up, I guess. And way out past these 4 terrestrial spheres, out past the moon, spun the stars, acting according to their nature as ethereal, or perfect circle-moving objects. And nowhere, anywhere in this theory, was a void. Nature abhors a vacuum. In Aristotle's cosmos, all of the elements were actively trying to get back to their natural states. Why did flames rise? They were just trying to get back to the fiery celestial realm above the air. Thanks, Thought Bubble. From the pre-Socratics to Plato to Aristotle, we've ended up with a bunch of spheres inside spheres, each with a natural tendency. This confirmed the average Bronze Age farmer's experience, and ours. The Earth seems to stand still, water sits on Earth, air isn't very heavy. Aristotle recognized that elements didn't always exist in their pure forms. A tree, for example, was a combination of earth, water, and air. Roots go down into the earth and branches go up into the air. His theories also worked for comparisons. Why does a book fall faster than a piece of paper? Well, because it has more earth in it. Aristotle could even explain natural phenomenon. Why does rain fall from the sky to the ground? Why do volcanoes shoot fire up? Obviously, this isn't how I think gravity works, but it's a way of explaining it that made sense to the ancient Greeks. Where Plato saw a world of ideal shapes, Aristotle had a theory that acknowledged that we're all kind of a hot mess. Things are naturally jumbled up, but always trying to get back to their essential place.
Now, all material is made out of these 5 elements, and they combine in different amounts to make the things that we have. For example, something made out of wood, it's made out of earth, fire, water, and air in a specific amount, and if you destroy that wood, some of that water gets released, the fire gets released, it rises up, smoke comes out, that's the air being released, and you're left behind with a little bit of the earth, which is the ash that's left behind. So this kind of explained, if you could destroy things, the 4 elements that were in it. There was no ether in there, but basically everything's made out of these elements, and you can kind of destroy them and break them down and see these elements in there. This made sense to people. Now, we now know this is wrong, but for 2,000 years, people believed Aristotle because they could see the evidence for it, like breaking it down like wood, and it contradicted what Democritus' idea was, is that it would be made out of tiny little wood particles. Okay, if you can break it into other particles of ash and water and things like that, then it kind of contradicts what Democritus thought. So people had this idea of the 5 elements in their head for a long time and hard to get out of. Then, in the Middle Ages, we had this thing called alchemy. Okay, they first started in Persia, but then the movement kind of migrated to Europe. This was a profession which focused on trying to purify things. They wanted to purify things and take things that were valuable, purify them, and then be able to sell them. They wanted to extend their own life. They wanted to turn one thing into another. For example, lead into gold is a famous one. It's called transmutation, by the way. They were not very good people, and there was just a bunch of people who were usually trying to study things to get rich. Okay? But the important thing is they carefully studied a lot of different materials. Even though it was kind of a hokey field of study, they studied things. And that means they were accumulating evidence about matter and actually learning a whole bunch of things, even if they were doing it for other reasons and they didn't really do it in a scientific way. But they actually started learning a whole lot of stuff. Eventually, alchemy transformed into chemistry as we became a science and we adopted the scientific method. Alchemy, chemistry, the words are actually related. Okay, so because of them, we realized that Democritus was more right than wrong, but Aristotle is actually pretty right too. Okay, so in our modern times, we consider both of these ideas, Democritus and Aristotle, as having merit. Stuff is actually made out of atoms like Democritus thought, but stuff also combines to make other things, and we have specific elements that combine to make those things, right? The particle nature of it. So Aristotle was kind of right about elements, just wrong about which elements, and Democritus was right about atoms. There's just not an infinite amount. So let's talk about these particles. So if we were to imagine a solid, a liquid, and a gas particle, tiny little atoms there, they can change into each other. Here's sort of a diagram of the particles changing into each other. So gas particles, they'd be all spread out. Liquid particles, they'd be closer together, but they're moving around. And then solid particles, they are kind of stuck together. So this explains what we see on our level by how those particles are interacting with each other. Now, before you copy these pictures down, there's something really wrong with this picture. Okay? What's wrong with it is actually the difference between solid, liquid, and gas. It's really close, but there's one small thing that's really, really wrong. Here's a much more accurate depiction of solid, liquid, and gas. Okay, this is actually solid, liquid, and gas for water. Now, if you notice the solid one, the one way over here on the left, they're actually pretty spread out. When they line up as a molecule, they actually form these empty spaces in between the molecules, which spreads them out, and that ice expands. Okay, ice kind of expands when it freezes because they kind of arrange themselves and create these structure where it is expanded and there's empty space there. As a liquid, though, because they're not structured and they're moving around each other, they are actually closer together as a liquid. So if I go back to this original picture, that liquid is wrong. It should actually be a little bit closer than the solid, not further apart. Okay? It should actually be a little closer than the solid. The solid should be a little more spread out. It's just rigidly in place. So the difference between a solid and a liquid is actually not spacing. It is how they're moving. The liquid, they're moving around. The solid, they're stuck in place and they're rigid. And usually the solid's actually more spread out because of that rigid structure. Okay, now a gas, on the other hand, they are spread out. Right? Gases, they go from liquid and they're moving around, and they're still moving around as a gas, but they go way spread out. Okay, so the difference between a solid and a liquid is their motion. Liquids are moving, solids are not. Not how they're spaced. I want to make that clear. The difference between a liquid and a gas, though, that is how they're spaced. They're both moving, but gases are much more spread out. Okay, so if you want to copy a picture, copy that one. Now, density. Density is an intensive physical property. I want to talk about it for a second. So I mentioned it earlier. It is the amount of matter in a given space. Okay, it's how much stuff you have packed into the same amount of space. It's the spacing there. So since we're talking about spacing with gases and liquids, I just wanted to mention this. So if I were to try and draw a particle picture of these three objects that I have on the screen. Okay, first off, let's draw some atoms here for this first object, and let's say it looks like that. Now its mass is 10 grams, its volume is 10 milliliters, so its density would be 1 gram per milliliter. The amount of stuff, the mass, how much space it is, the volume, okay, how packed together that is. That's what density is. Now, this next object has the same volume. It's exactly the same size, 10 milliliters, but it has more mass, more stuff packed into there. So if I were to draw a picture of this, I would have to have more material in that box. So I would need more particles, okay, packed in there. I could also have bigger particles packed in the same amount of space, but the idea here is there's more material in that space, okay. This third object here actually has more volume, but also has more mass. Okay, so there's more space, but there's also more particles. So if I were to draw those, I have twice the mass as the first one and twice the volume as the first one. So I have essentially the exact same spacing as the first one, even though I have twice the material. It takes up twice the space, but the spacing is the same, so the density is the same. Density for the first two objects is identical, but the middle object, density for the first and the third object is identical, but the middle object, that's a different density, so it's probably a different material. Since it's an intensive physical property, I would say that the first box and the last box are probably the same thing, same material, because they have the same density, 1 gram per milliliter. Okay? In fact, if I kind of cut it in half, you can see the two boxes are basically the same. Okay? Now, to calculate density, because there's a calculation involved, yes, mass and volume are extensive properties and density is an intensive property, but you use the mass and the volume to calculate the density. So density is mass divided by volume. Okay? D equals M over V. Mass divided by volume. So we're going to do a calculation here. So calculating density. I've got the formula here, mass divided by volume, just for reference here. So let's take an example. We've got a golf ball. Its mass is 45.3 grams. Its volume is 40.48 centimeters cubed, or milliliters. So density is mass divided by volume. So in order to calculate its density from these extensive properties, I take the mass and I divide it by the volume. So the mass divided by volume equals 1.135 grams per centimeters cubed. Okay, now significant figures there because the calculator had a whole bunch of them. a whole bunch of digits. My mass has 4, my volume has 4, so my answer has 4. Okay, your turn. A baseball. A baseball has a mass of 145 grams. Measured it, threw it on a balance, there it is. And it has a volume of 195.43 centimeters cubed. Threw it in some water, the water level rose, measured that one. Okay, so I got the mass and the volume. Pause the video, figure out its density. Okay, so the density of the baseball. We take the mass and divide it by the volume. So 145 grams divided by 195.43 centimeters cubed. And we get 0.742 grams per centimeter cubed. The 145 has 3 sig figs. The 195.43 has 5 sig figs. So our answer rounds to the lower 3. So it only has 3.742. Some more examples. So you can actually figure out the mass or the volume if you know the density. First example here, what's the mass of an object that takes up 575 centimeters cubed and has a density of 3.97 grams per centimeter cubed? So I know the density and I know the volume. What's the mass? I can find the thing I don't know. So if I rearrange that equation, D equals M over V, if I rearrange it for M, it would look like this. Okay, M equals density times volume. So, to find the mass, I take the density, 3.97 grams per centimeter cubed, and I times it by the volume, 575 centimeters cubed, and I would get 2,280 grams, rounded to 3 sig figs. Okay? Second example. What's the volume of an object that has a mass of 9.56 grams and a density of 1.74 grams per centimeter cubed? Okay, so this time I have the mass and the density, and I want to know the volume. So density is V over M. So, excuse me, density is M over V. So rearrange that equation for volume, find the density. Pause the video and see if you can give this a try. Okay, so the volume here, if I rearrange it for volume, I would get mass divided by density, right? So the volume is the mass divided by the density. So the mass is 9.56 divided by the density, which is 1.74 grams per centimeter cubed. Volume is 5.49 centimeters cubed. Now density is always going to be the same for the same material. It's an intensive property. So even if it has a different mass or a different volume. So if I had 5 objects that were all the same material, but they had different masses and different volumes, they have to because they're different sizes, all right? Figuring out the density of this object, 15 grams divided by 2 centimeters cubed, 7.5 grams per centimeter cubed. I do it again, but a bigger object, 60 grams divided by 8 centimeters cubed, same answer, 7.5 grams per centimeter cubed. Doesn't matter how big it is, it's still 7.5. Still 7.5, still 7.5. The density is always going to be the same because it's a relationship between those mass and the volume. It's a relationship between the spacing. That's what density is. Okay, so it's always the same for that material. Okay, now if we were to graph the mass and the volume of this, all right, so I have these 5 size objects, the mass for all of them, the volume. If I were to graph them on this, volume on the x-axis, mass on the y, okay? I put those dots right there. That first one is 2 centimeter cubed and then 15 grams. There's that first dot. All the way up to the biggest one, 100 centimeter cubed and 750. Okay, you can see a very straight line relationship here. All right, that straight line, if I were to actually find that line, it would be y equals 7.5x. Density is the slope. It is the slope of this line comparing volume and mass. Okay, so if you were to graph this, you could actually use this graph to also find the mass or the volume of an object. For example, what's the mass of an object that has a volume of 28 centimeters cubed if the density is 7.5 grams per centimeter cubed? So I've got this line here. Slopes the density right here. Okay, I want to know what its mass is. And I don't have to do any math here. I just got to look at this graph. Volume, 28. So 28 is around here. Go up to the line. bam, it's a little bit higher than 200. If I were to actually measure it carefully, it would be 210 grams. Okay, and if I did the math with the equation, yep, that's what I would get. So 210 grams, 28 right there, just above the 200 line. Okay, and that's it for the notes today.